All right, so now welcome to this video. Now in this video, what I'm going to do is I'm going to continue off where we left with pure substances. We're actually talking about the phase changes of our pure substances, right? So we looked at these diagrams and how these diagrams actually correlate with one another. What's the relationship between these all of these diagrams that we see over here? How can you see this on which graph? Please refer to the previous lesson, okay? And therefore, we spoke about the change of phases or the change of states from solid to liquid. Actually, we started from liquid to vapor, right? And therefore, here's the graph that shows the relationship between the pressure and the temperature. It is called the PT graph. We spoke about that as well. And then we also looked at this diagram towards the end, where we spoke about the naming of these pure substances based off the temperatures, right? When the temperature is equal to 20 degrees, this will just be called the liquid. But when the temperature, it is actually greater than 20 degrees, but less than the boiling point, we're gonna have what type of liquid in the container or into the cylinder or in the piston. We're gonna have the subcooled or the compressed liquid, if you still remember that, right? And therefore, having a look at these three diagrams, they actually symbolizes the same thing. Look at the temperature, we have 99.6 degrees, 99.6 degrees or 62 degrees, 99.62 degrees. These three diagrams, they actually talk about the same temperature. So what's different about them? So here we have the liquid and then here we have the vapor. Look at the volume and look at the volume over there. The volume, it is less over here. The volume, it is greater over there. And then here we have what you call the equilibrium. Let me re-explain this because this is what I'm going to redo, but explaining that graph that I said I will explain on this during this session. So now when the temperature reaches the boiling point of our pure substance, in this case, our pure substance is water. So in this case, we're gonna have saturated liquid. The moment we include the word saturated, that means it is liquid mixed with water vapor. But you have to understand when we have at the beginning, whereby our quality is a little bit less. I'll explain the quality part even on this lesson. But when our liquid reaches its maximum boiling point, therefore, what are we going to say? We have the saturated liquid. But at that maximum boiling point, let me go back to this graph. At that maximum boiling point, which is here, the boiling point will remain constant for quite a while. So when the boiling point remains constant for quite a while, you need to understand that the volume is actually increasing from this point to that point. The volume is increasing. Like I said, look at the volume over here and look the volume over there. You can tell that the volume inside of the piston or inside of the container, it is actually increasing, right? Like you can even see on this diagram over here, the volume, it is actually in, okay, let me take it to here. I'll come there. To here, the volume, it is actually increasing while the temperature is the same, is the constant, right? So you need to understand that at boiling point, the liquid will get to be transferred into vapor. It's a transformation process. It's a transformation process of the phase change. You understand? So that means, and then in this diagram over here, we have the equilibrium whereby the rate of the vapor is equal to the rate of the liquid. So here we have the vapor and the liquid at equilibrium. Here we just have the saturated liquid water. And in this side, we have the saturated water vapor. We no longer have liquid at all. The liquid has already evaporated, meaning the liquid water, it has now turned into the water vapor. Now we can see this is where the completion of phase change, it is actually taking place. You understand? At the same temperature, because this is the maximum temperature at which water boils. But if we keep on increasing by heating the system, if we keep on increasing the temperature of the system, we can see that the temperatures that are above the boiling point, most of the time, water cannot boil after that, but depending on the pressure, because we have the pressure that is fixed at this point, we have 100 Kelvin pascals, or 0.1 megapascal, which correspond with 0.1 megapascals. At these lower pressures, when we keep them constant and we further heat the system, therefore, the saturated water vapor will turn into superheated vapor. Meaning the superheated vapor, it is the vapor that it is not about to condense, so this vapor won't condense at all. So that's what we actually spoke about last time, right? I'm just re-explaining this because I will be doing the exact same thing, but now graphically, okay, using this graph over here. Now, using this graph, we spoke about A, B, C, D. Remember, from point A, it is whereby our temperature was 20 degrees Celsius, if you still remember. And then our temperature over here, it's going to be 99.62 degrees Celsius, right? And if we look at here, this is the equilibrium. So here at equilibrium, we can tell that there is a process of a completion of the phase change, meaning here we have the saturated liquid, and then this side we're going to have the saturated vapor. Why do we call them the saturated? Because they are mixed up together. Saturated liquid, it has vapor in it. Saturated vapor, it has liquid in it, and so it is called saturated. You understand what I'm saying? So this one over here from C to D, we no longer have saturated vapor, rather we have the super heated vapor, meaning this is superheated vapor. Is a vapor that you see the temperature, it is now further increasing, but here the temperature was constant throughout, which was 99.62 degrees Celsius. But when we further increase our boiling point temperature, we can see that we're going to have superheated steam. Okay, so again, this is what I want you to understand about this diagram. Having a look at this line over here, these lines, A, B, C, D, this line over here, we call these lines the what? The isobars. Why do we call them the isobars? Because they maintain constant pressure throughout. But you need to understand that the pressure at this point was 0.1 megapascals. So when we increase pressure to 1 megapascals, what's going to happen? Now we're going to have our substance starting from this point, which is point E, F, G, and H. Whatever I explained over here, it is the same as what it is actually going to take place over here. But the difference here is we can see that when the pressure gets higher, the starting specific volume gets lower. You can see that our specific volume here, our volume here for A, it is less. But have a look at the volume of E. It becomes, the volume of A here, it's this one. And then the volume of E, it becomes lesser than the volume of A. The volume of I becomes lesser than the volume of E. The volume of M becomes lesser than the volume of what? The volume of M, which is here, it becomes lesser than the volume of I, and so forth. Why? Because the pressure, it is further increasing. So now you can also talk about the relationship between the pressure and the volume. Just looking at this graph over here, you can just analyze this graph to talk about that. And then not only pressure, it is decreasing when we increase this, not the not the volume is decreasing when we are increasing the pressure. We can also look at the relationship on this graph. We can also look at the relationship between the pressure and the temperature. Look at here. The boiling point here at B, it is 99.62 degrees. But look at here, what is the boiling point? It is more than 99.62 degrees. It could be 300 and something, 362 degrees, 313 degrees. It is above 99.62 degrees. So the temperature over here, it is high, meaning for us to turn at the high pressures, if we take water, at the very high pressures where we increase the pressures, we need to understand that the equilibrium temperature or the boiling point of the temperature will have to increase. You understand? The more we increase the pressure, the more temperature we need to boil water. Because if we have this pressure over here, which is 1 megapascal, and then we give our water the temperature of 99.6 degrees Celsius, you can see that the water won't boil at pressures of 1 megapascals. The water will only boil at these temperatures, maybe 319 or 300 and something, 311 degrees Celsius. At 311 degrees Celsius, that's when the the liquid water will start to will boil at about those temperatures, 311.1 degrees Celsius. Therefore, water will start to boil only if the pressure is above 0.1, like 1 megapascal. The further we increase the pressure, right, the more we need the boiling point, the more we're gonna have to increase the boiling point of our water. If in this case our pure substance is actually water, so the pressure further increases, the temperature is supposed to increase, which is true. We know that the more temperature, the more the pressure we're gonna have, right? So that's what is basically happening. But for one system per se, we keep the pressure constant. Like here, we keep the pressure constant. But if we consider different systems, system A, system B, system C, system D, having different pressures, therefore the boiling points are not going to be the same at all. Right. So the another thing that I want to explain on this graph is now, like I said, this graph, this one, they're gonna do the same thing. The difference is what I've just explained, the increase in temperature and decrease in the volume. That is the only thing. Now I want us to talk about this graph over here, which is called MO. Okay, we are focusing now on this isobar over here, MO, whereby the pressure is very high. The pressure, it is 22.09 megapascals, right? So now this pressure over here, when we have high pressures like this, yeah, so we're gonna have what you call the critical point. By the way, do not forget this side over here, this line, this equilibrium line over here, what does it indicate? What does it indicate? It indicates the saturated vapor line. It is called the saturated vapor line. And then this line going downwards, it is called the saturated liquid line. So this is the saturated vapor line, and this is the saturated liquid line, okay? So now at the peak of these two lines over here, we're gonna have what you call the critical point. So now what does the critical point mean? Now, when we talk about the critical point, let's discuss the critical point together. So when we talk about the critical point, which is this maximum peak over here, it is whereby most of the time the critical point is the point at which the liquid and vapor phases are not distinguishable because of the liquid and the vapor having the same properties, which is true. So remember, let me take this line once more again. Let me explain this line once more again. So when we talk about this line, this isobar over here, we can distinguish two phases of our pure substance. At point B, our substance, it is liquid that is saturated. At point C, our substance, it is vapor that is saturated. Okay? You can see that the more we increase the pressure, the more this line gets shorter of equilibrium until we have none. We're going to have point of inflection over there, whereby there is no saturated liquid, there is no saturated vapor. You understand? So at that point, we say that we cannot distinguish whether we have the saturated liquid or the saturated vapor, because how can we see that? Here it's easy. We can see here vapor, saturated liquid, saturated vapor, saturated liquid. The more we go high, until we cannot distinguish between these two guys over here, because it's like they're mixed up together, they are meshed together. So that's what we call the critical point, okay? So at the critical point, we have what we call the critical pressure, we have the critical temperature, we also have the critical pressure at the critical point. So 22, sorry, let's see. So 22.09 megapascal, it is called the critical pressure for water. And then the temperature over here, it will indicate the critical temperature for water as well. Okay, so always know that at the critical point is where we cannot distinguish these phases, the liquid phase and the solid phase. We cannot distinguish them. We say they have the same property at the critical point. What? The liquid and vapor have the same properties. But here, they do not have the same properties, referring to their qualities. I'll explain qualities to you further later on during this session. Okay, so that's what we mean by the critical point. So now having a look over here, we have a table that shows the criticals for each and every pure substance. So we just spoke about water, right? We saw that the critical pressure for water is going to be 22.09 megapascals. But now the temperature will be 374.14 degrees Celsius. So we can see that at critical point, we need very high pressures and very high temperatures. Can we see that? And then another pure substance that we can talk about is carbon dioxide, right? Having a look at this number 2, which is carbon dioxide, we have its critical pressure. We also have its critical temperature. So meaning if you take carbon dioxide in a piston or in a cylinder and you maintain a pressure at 7.39, and then you supply a heat that will maintain, that will give a temperature of 31.05 degrees Celsius, we're going to have the critical point, meaning we won't be able to tell whether we have the vapor or whether we have the liquid, right? You cannot distinguish them, you cannot differentiate them, right? So at that point, we say we have the critical point, and the properties of the liquid and the vapor are exactly the same. You understand what I'm saying? And same applies to the oxygen, same applies to the hydrogen over here. So that's it about that line, which is called line MNO, that has the critical point, right? Now let's talk about this line over here, which is called line PQ. Now, what is happening with line PQ? The line PQ, it is not in contact with our dome whatsoever, right? So line PQ is not contact with. So what we mean, like what we call this line, what is the purpose of this line? You see, it has a very, very high pressures compared to the other isobars. So the pressure for this line, it is 40 megapascals. That's a very high pressure, right? So at this point in time, we're gonna have what? What is the name of this line? What is the purpose of this line? Now, this line, it represents the pressure above the critical pressure. So it is the line that has a pressure that is most definitely above the critical point, right? So what, remember, the purpose of us talking about these lines, we're talking about this, let's say we're talking about water, we're gonna talk about the phases of water, right? So having a look at line PQ, what phase do we have? Do we have vapor? Because remember here already, we're not able to distinguish the vapor and the liquid. But line PQ, because it's more than the criticals, then what's happening there? So here we have what you call the fluid. At this point in time, we say that PQ represent the pressure above the critical pressure. And then the fluid or the pure substance, our pure substance at that point, it is considered or it is regarded as a fluid, right? Why do we call it a fluid? Because we cannot tell whether it's a liquid or it's a vapor state. So rather, would rather call it the fluid at that point. Hence why here we say we have what you call the fluid region, which is the region of a higher temperature and pressure than the criticals. Can you see that? And it's termed supercritical. So meaning at this point, the fluid region, it is called the supercritical. It is no longer critical, but because it's above, it's superior over critical, therefore we will call it the supercritical. So at supercritical, it's whereby we have the fluid region. So you won't be able to tell whether this is vapor or liquid. You can't tell, we just refer to that as fluid. Okay, so that's what is basically happening. Now, having a look at TV coordinates for saturation conditions. Now, I want us to discuss this thing of saturation so that we can understand, okay? Now, what I'm gonna do is you can take this portion or you can take this portion. It does not matter. You can take this part or we can talk about taking this part. It is the same as what we see over here. But here I want to talk about the saturation conditions. Now remember, there is that line over here, if you remember, and then this is the isobar, say our pressure here is 0.1 megapascal, right? This is the same as what we looked at. Now I want us to talk about the saturation conditions, right? Remember, I said to you here, we have the saturated liquid, and then here we have the saturated vapor. And then this V, and okay, I'll explain this later on. So now look, Here we have the saturated liquid. So what does that mean? I said saturated. It is a mixture of liquid and vapor. Same applies to here. So now we have X. X, I said to you, it refers to quality. Quality. So what does the quality mean? It means mass vapor fraction. Mass vapor fraction. Okay, quality refers to the mass vapor fraction. So now here our X at this point, at saturated liquid, our X is equals to 0. Why do we say our X is equals to 0? Because at this point in time, we still have the liquid, right? But the moment when we shift to the right a little bit, maybe somewhere here, whereby our X will start to increase, maybe our X at this point will be 0.0001 or 0.1 or 0.2, whatever the case could be, as long as we have a number that is above 0 over here, which is our value of X, then that's where we can talk about the pure saturated liquid, because now we can see, we will know that our liquid, it is now composed with vapor as well, or it is composed with gas as well. So that means at this point, our X is 0 because I'm saying to you, X, it is the mass vapor. So at this point, we have the pure liquid. We do not have vapor yet. So that's why we're saying X is 0, because to determine X, which is mass vapor, we're going to say X is equals to mass of a vapor, right, divide by total mass. So when I say total mass, what is total mass? Total mass, it is the mass of the liquid and the vapor. So this is the mass fraction. You understand? So mass fraction refers to the quality, which is denoted by variable X. So at this point it's 0, but the more we move towards the right, the X starts to increase. And then at this point, where is the middle point, our X, it is at the equilibrium of mass vapor and liquid. So at this point, here we have 0.5 VF, we have 0.5 V V what? VG. G is for gas, okay? And then F is for fluid, for liquid. So at this point in time, they are balanced. It's 0, 0.5, 0, 0.5. The more we move to the right, 0, 0.8, 0, until we get 1. So when we get to 1, here we have the saturated vapor. Now we can also have the vapor that is mixed with liquid. But when we say X is equals to 1, because this is where gas actually belongs compared to the X, now it is completely describing what is the quality is mass vapor. So meaning X at this point, because it's 1, we have the mass vapor at this point in time. Okay, so that means the more we increase the temperatures, and then we have this line over here, we'll no longer have X. X cannot be greater than 1. So here we'll no longer have X because we have the superheated. We no longer have the mass vapor. We have the superheated steam. Okay, so that's what this coordination actually talks about. So VF, it simply denotes the specific volume of fluid or liquid at this point. And then F, it denotes the properties of a liquid. And then FG, it simply denotes the specific volume of the vapor at this point. And then subscript G, it denotes the properties of vapor. So that's why I was saying to you, the properties of vapor at this point, it is 0. You don't have the properties. But here we can see that the properties of here at this point, maybe somewhere here, we have the mixture of liquid and gas, but we have more of liquid and less of vapor. Here we have more of liquid, less of vapor. Here we have 50%, 50% liquid, 50% vapor. And then here we have more vapor than liquid. Here we have more vapor than liquid. Here we have vapor. You understand? But we will call it saturated even though X is 1. Here we'll call it saturated liquid even though X is equals to 0. Because this is where the states are about to change. So here it's liquid, and then there we're going to have gas. Simple as that. Okay. All right. So now here we have the equations that we use to perform the calculations. Most definitely, we're going to look at the calculations. and the tables. We're going to look at the steam tables. So at this point in time, when you talk about the volume, it's simple because we're talking about two phases, which is liquid and the vapor. So when you want to determine the total volume of the whole system, you're going to say volume of the liquid plus volume of the vapor, right? So, but you have to understand that the formula that we use to calculate the specific volume, you can denote your specific volume like this, not like this. You can denote, I'm struggling to draw this all the times. You can denote your specific volume just like this, right? Your specific, or you can just put a cap on top. I prefer to do this one. So you can denote your specific volume like this, right? Specific volume, remember the units for specific volume, we use meter cubed per kilograms, right? So that means if we take volume and then we divide our volume by mass, we're gonna get the specific volume. So now, if we want to denote this by specific volume, if we want to know the total volume by the specific volume, what are we going to say? Okay, so I see here V is equals to V of the liquid plus V of the vapor. So now, how to substitute, how to make this subject to the formula? How to change this into mass vapor? Remember, in order for me to get the V, I'm going to have to take mass and specific volume. So if I multiply mass to my specific volume, I'm going to get the volume. Do you agree with me? Because mass, it's kg, right? Multiply by specific volume is meter cubed per kg. So the kg will cancel the kg, and therefore I'm going to left with volume, which is meter cubed. So in order for me to get the volume back, to get this volume, I'm going to have to multiply specific volume with my mass. Can you see that? So here it's for liquid, and then here I'm going to say mass specific volume for vapor, right? For vapor, which is the same as this over here. So mass of the liquid multiplied by the specific volume plus mass of the vapor multiplied by specific volume of the gas. Remember, GF denotes liquid and then G denotes vapor. So that's how we go about for calculating the volume. Now, this formula is what I've spoke about when you want to do the calculations, but you have to understand that here, for mass of the liquid, rather we're going to use the specific mass. We're going to use the mass fraction. Remember, I say to you the mass fraction, when you take your mass total, which is given by mass of the liquid plus mass of the vapor. This is the mass total, right? We have the mass of the liquid, we have the mass of the vapor. So if I want to determine the fraction, mass fraction for liquid, I'm going to say mass fraction for liquid is going to be mass of the liquid divided by the total mass, right? If I want to determine the mass fraction for gas, I'm going to say mass fraction for gas or vapor divided by total mass. So meaning here for mass of the liquid, and then here for mass of the vapor, we're going to introduce the fraction over here. Can you see that? We're going to introduce the fraction over here. Even this side, remember, we're going to have to remember the specific volume multiplied by volume. We're going to get the specific, we're going to get this over here. Okay, I want to do it like this. We have the total volume, right? We have the volume of the liquid plus we have the volume of the vapor, right? So now remember this, how can we change this using the specific volume? Remember, I said to you to get the volume using the mass and specific volume, you're going to have to multiply total mass, because remember, this is the total volume. Total mass multiplied by the specific volume, right? Total specific volume will be equals to, even here, we're going to say to get the volume of the liquid, we're going to say mass of the liquid multiplied by the what? By the specific volume of the liquid. Okay, I'll just write F over the fluid. Plus mass of the vapor, it's going to be mass of the vapor multiplied by the specific volume for what? For gas in this case. Remember, this will take us back there when we perform this calculation, right? And then now, what I'm going to do is I want to make my specific volume the subject of the formula. So that means I'm going to have to divide by mass. So when I divide both sides by mass, now I'm doing it mathematically. I'm going to I'm going to have this. It's my up. Oh. So that means this side, when I divide both sides by mass, I'm going to have m of the liquid divided by total mass multiplied by the specific volume plus mass of the vapor divided by total mass multiplied by specific volume of the gas. And therefore the specific volume, total specific volume in this case, remember this, it will represent the quality, okay? So definition of a quality, which is X, it is mass of vapor. You understand? Listen to me, mass of a vapor. It's a mass of a vapor. So that means here I can have, let me show you something. This is the fluid, remember? Remember, mass of a vapor is going to be this side, meaning here we're going to have XVG, right? But you need to understand that the quality, here we're going to have 1 minus X. Why am I saying 1 minus X? Because referring back to this diagram over here, remember, I said quality ranges between 0 and 1, right? So when you have a mixture of gas, 60%, and then that the vapor will be 40%. If you have the mixture of a gas, a vapor of mass vapor to be 0.7, therefore the liquid will be 0.3. So that means here they're supposed to, when we add them together, they're supposed to give us 1. So the difference that we're gonna get, you're gonna say 1 minus the mass fraction for mass vapor, and then you will get 1 minus X. And therefore, this normally is a formula that we use to calculate the specific heats using the steam tables and so forth. But you will see how we go about for this, which is basically this equation over here, right? And by the way, this equation, it can be written as this one. The first equation, which is this equation, it can be written as this one. So to determine the total specific volume of the system, you can say this specific volume of the fluid plus our quality multiplied by the Fg. Remember what is the Fg? So a combination of what? Of fluid and the gas. Okay, so that's how we go about for this session. Then we'll meet again on the upcoming session. Thank you.